actually making sure that everything about the Gaussian model is absolutely clear, and parts of it which you will have to sort of, I will indicate the parts which you need to fill in carefully. Uh, so the point is that before starting out with the or rather leaving this particular issue for the moment, I want to make sure that Gaussian model is understood absolutely clearly, so that when I come back to doing the 5/4 theory, things are absolutely clear. So what the Gaussian model involves is a free energy which is quadratic. So it is ddx a over 2 pi square plus half gradient of pi square. I'm working with a scalar phi simply to keep the writing minimal. In general, phi square means phi I, and grad phi square is del j phi I, del j phi I. The calculations here will keep I equal to 1 and j equal to d. So it's a d-dimensional space, but the field is scalar, and nothing changes with the vector except the combinatorics. So the point with all these calculations is that it's stat mech, so I have to get a partition function. Partition function is e to the power minus beta and this integral over here. The A is A0 T minus TC. Our interest is entirely in is for, I mean, if I make it a TC over here so that it's dimensionless, T minus TC over TC much smaller than 1. That is the only range of interest. So there's this beta over here. The beta, which is 1 over kT, is really just 1 over kTc. So no temperature dependence coming from the beta over here. All temperature dependence is in this coefficient A, because my interest is entirely in T minus Tc over Tc and possible singular behaviors in T minus Tc over Tc. So that's my interest. So that is a very narrow interest over here. And therefore, I mean, that is what allows me to keep the beta constant. So it is, otherwise, I mean, it would be a mess. So anyway, so that's the point number 1. Now the thing is, this is doable. So this, I have missed the d phi over here. And this quadratic thing is doable. The answer is, at the end of the day, pi over all k. All k is legal in the sense of you imagine that it is all in a volume, and you can discretize the use boundary conditions, periodic boundary conditions, discretize the k, and talk about n times pi over L. And then when you are through, I mean, that is for understanding. And then when you are through and nobody cares, then your k is a continuous variable. So that's the accepted illegal maneuver. So and this works out to be 1 over a plus k square to the power half, and there is some numerical constant over here, numerical constant which will involve obviously the beta, and but that you can just fix it for yourself. We will never need it, so I'm not writing it. So z is equal to a string of factors which are square root of a plus k squared, and there is a numerical proof. So that is the basic integral that one needs to do, and one finds that this is this. Now the point is that this, however, while this is the basic integral that you need to do, the physical quantities are all related to moments. So the first thing is that I need to know is a 2-point correlator g of x minus y, which is the expectation value of phi x, phi y. So translational invariance, so you look all the single moments, this is quadratic over here, so all the single moments are going to vanish. So odd moments of phi vanish. So that's because of the phi square. So the first thing that, and the only thing that one needs to calculate with a Gaussian function is the 2-point function, which is so this is what we did. Calculations are done primarily in primarily in the Fourier space, and if I write the Fourier transform over here, then this would be ddk over 2 pi k, and then it is phi k phi minus k e to the power I k x minus 1 dot. So phi k phi minus k is what we calculated. All calculations can be done only in momentum space, and the coordinate space passage has to be through the Fourier transform. So phi k phi minus k, and therefore what we had to do is it is always defined as e to the power, it would be defined as 1 over z, just as any other expectation value, phi k phi minus k e to the power minus f, and then the d phi, and the z is this. So that's, and the answer was 1 over k squared plus a. So there would be prefactors over here as well, which do not carry any temperature dependence, and therefore, I mean, ignoring everything that all that can be set. I mean, we will, whatever comes as the prefactor over here, we will choose it to be 1, because that is how the constants will be. And so for future use, phi k phi minus k would always be 1 over k square plus a, with the constants that appear because of the floating betas and so on the pi's and the things like that which come along naturally, being set equal to 1, so that, I mean, this coefficient is always 1. So phi k phi minus k is 1 over k squared plus a, and that is what we will always use. That is the way the constants are, the normalization is done. So, so that is one. Now, the string of phi's one would need in general, obviously, phi1 to phi1, phi2 to phi2n plus 1, that is equal to 0. All odd strings vanish. But phi1, phi2 all the way up to phi2n, that has to factorize. So I go with, let's say, the 1, 2 to 2n over here means that the meaning of phi1 is phi of k1 and so on. So Gaussian integral will automatically lead to a factorization of these things over here. So when you write this string, which is, let me give you the thing over here, and I have on the top, I have e to the power things phi k1, phi minus k1 minus phi k, so minus plus over here, phi k2, phi minus k2 plus similar things. So this, it is split over here. All the k's are independent of each other in the numerator over here. This will not happen as soon as if I added a 5/4 term over. It is a specialty of the Gaussian, which says that all these chaps, the prefactors, are also their own. I mean, this comes with the prefactor a plus k1 squared, this comes with a plus k2 squared, and so on. So all the k's are separated out, and therefore the integrals are all separately doable. But separately doable in what? That I can connect k1 and k2. For these to be valid, I would for these to give me non-zero answers, one pair k1 k2 has to couple and the other pair k3 k4 has to couple. So this, and when I did not have the coupling, that is, if I did not have this chap over here, the answer is 0. So you can do the coupling in all possible ways. It can factor in this way. It can factor in this way, or it can factor in this way. So there would be 3 possible factorings of these 4 chaps over here. And so if I have a string, then it is all possible factorings which, now why is this? This is extremely important, and this is what, I mean, this is where you should check out very clearly for yourself. Yes, sure. Yes, sure. Yeah. Fine. So, yeah. This is, I mean, which you need, the test which you should carry out for yourself, that is certainly important, that the specific heat, when we talked about the specific heat was the correlator ddx1 phi square x1 ddx2 phi square x2, that correlate, that expectation value. And so we had to get this chap calculated. So it was a question of calculating integral ddx1 ddx2 average of phi square x1 phi square x2, and that would have to be, I mean, well, there is the z at the bottom. So this is, I mean, sorry. So it is dx1 dd2 e to the power, and then this is it's the d phi over here. It is e to the power minus integral the phi over here divided by the z square over here. The phi square x1 phi square x2 will be exact, I mean, will have to, if you write out the Fourier transforms, would be looking like for the four of these, which, as I told you, would be you would have to take care of the three possible factorings. Now the specific heat was, mind you, not just this. It had a minus, and the minus was the square. The integral ddx phi square x, that average square. So you evaluate this one through this technology over here, taking all possible combinations, and then remove this part over here, and at the end of the day the exact answer should be integral ddk 1 over k square plus a whole square. So this is the exact form, and you get that exact form only through the cancellation over here. I mean, if the specific heat did not have that in the definition of the definition, meaning, I mean, calculating del 2f del t square, if it did not have this cumulant removing part, then you would not be coming up with this clean expression that it is a ddk over 1 over k square plus a whole square. So the part of the baggage essentially of having these kind of local, see this, what has happened is that the non-locality over here, which is vital, the phi square x1 and phi square x2, you are really doing a correlation function, it contains in it a local part which you are separating out. So you are looking at the fluctuating part, getting rid of this part. That is when I look at something like the fluctuation, which is, I have a magnetization, let's say uniform, the system is below TC, then this phi over here would have to be, the fluctuating part is minus the expectation value, which is equal to phi minus m. Above TC, I never worry about this. So this Gaussian model, I did not have to worry. It is all above TC. So I never really worried about removing the expectation value from this. And if I did not, when I do have the expectation value, then if I don't remove that expectation value, then the point is that you would be having extra, the free energy, which is this phi square grad phi square, would now be give you expectation value of phi if I'm as written in this form over here. I mean, the phi square plus grad phi square, and if I add a phi 4, is incapable of giving you an expectation value, right? So incapable of giving you an expectation value. So in that form, I cannot use it below TC. And if you have to go below TC, you better watch out, because below TC, this becomes a minus and therefore is a potential problem. And the way you get rid of it is by subtracting the expectation value, because the whole business of this becoming minus is actually giving you a transition and an expectation value. Yeah. So you have, so when I'm looking at just the phi field, I have to remove the expectation value, and if I go below TC, that is when A becomes negative. Otherwise, over here, because I'm talking about phi square, you have that same issue above TC. The quantity, the physical quantity, is this expectation value minus the sort of trivial part, which is just the local quantity subtracted out. But this subtraction is, and this subtraction is physical. That is what the specific heat is. It is not just this, it is this minus this, and only then you are going to pick the answer up as this quantity over here. So it's extremely important that you actually work it out and make sure that the three terms that you are going to get from here are, two of them actually get cancelled out by this, and only this chap remains. Huh? Below TC, see, you have a problem, because if you were to take blindly below TC, the whole idea is that I have a magnetization, right? That means that phi average is not equal to 0, right? But I told you that this quadratic or even terms in phi square, and if I try to calculate the average value, I should be getting 0. Now, why is that not true below TC? Below TC, it is not true because this coefficient is going to become negative and the integral is no longer well defined for all values of phi. And then if I have to set it up correctly, I would have to remove, it's not working because with a quadratic term, I should not be, with an even phi field, I should not, so long as the system shows the phi up, phi down symmetry, plus minus symmetry, I expect average phi to be 0. But the physics says that the average expectation of phi is not 0. So in order to resolve this, I actually need to work in terms of a field where the expectation value is removed from it. Yeah.
The whole aspect of seeing that below TC that Gaussian model does not work.
Yeah.
Is that we go to the liquid and then then extremize the free energy, and we get the magnetization must be 0.
But only because you have the m to the power 4.
Because
yeah.
the m to the power 4, 5 to the power 4 term is therefore the only solution is n is equal to
0.
But if we don't see the problem in the mean field, then how will you say that we see that it is not wrong?
But you can't do mean field theory with this free energy. There is no mean field theory.
And then say phi to be m, second term vanishes.
Right. So it's just m square.
The m square, yeah.
So no expectation value.
Yes. So M is now.
M is equal to 0.
Yes, sir.
So no transition.
Yes, sir. So, but that is NFT. But other than NFT, that is observed.
No, but MFT is mean field theory gives you no transition. So if I'm going to use a Gaussian model, there is no mean field theory transition. M is always 0, identically 0. So there are only fluctuations around M equal to 0, and that is what you are calculating in the Gaussian model, that you are above TC, M is equal to 0, you are calculating the Gaussian fluctuations.
You have to use that, you have to replace phi for phi minus x.
You're right. So you introduce a field psi whose expectation value by definition is 0. And then rewrite this, plus the phi 4 in terms of the psi for which the expectation value is 0, and then go ahead and do whatever you want to do.
You said that for Gaussian case, the A becomes negative and the integral is not defined for particular. So can you give an example?
It's e to the power minus. That is e to the power minus f. So if this becomes
Minus the plus and the
Right. So so this is, the thing which I wanted to make sure that you actually do this carefully and make sure that the answer is really this. That's important. It will give you confidence that and so this is the so now all right. The last bit that needs to be said about. So what is the next thing about Gaussian integral? That I need to know what is the answer for and that breaks up into phi k1, phi k2, into this up to phi k2n minus 1, phi k2n, and then you would have all the possible permutations that this goes with, for example, maybe the third one and so on, plus all the permutations. So that is the answer. So that completes everything that you need to know about the Gaussian model, that these are the answer for the 2-point function is this. The answer for the 4-point function is exactly this. And the higher order functions, when you want to do, are going to come up. That is this particular 4-point function, the answer is exactly that. All right. So now comes the next issue. One still within this, there was something else. Yeah. Back to the Gaussian and looking at a couple of other things. That phi k, phi minus k, as we agree, is 1 over k squared plus k. So what often you need not the k-space answer, but the coordinate space answer, the Green's function g of x minus y. That is the correlator in real space, phi x, phi y, and that's your g of x minus y. And g of x minus y, we have learned is, let me call this x12. So x1, x2, and g of x12 is integral e to the power I. So this is a vector. It will be a function of the scalar part, but in general, it is going to be a vector. And then it is the phi k, phi minus k. So that is your g of, that is gx12 is the Fourier ddk divided by 2 pi to the power d, that times the g of k. And the answer for it is integral ddk over 2 pi to the power d e to the power I k dot x12 divided by k square plus c. All right. So now let's see what you remember. D equal to 3. What's the answer?
স্যার ওটা 1 বাই mod x এর মতো ফল করবে না? আমি শিওর নই, মানে
1 by
mod x, আমি শিওর, মানে গ্রিনস ফাংশন ফর মানে 1 বাই k স্কয়ার প্লাস a, তো k প্লাস i a k মাইনাস i a তে পোলস গুলো থাকবে তার, আর তারপর
হ্যাঁ, সো তাহলে উত্তরটা কি রকম দেখতে হবে?
স্যার 1 বাই mod x, স্যার কুলম্ব ফাংশনের মতো
Coulomb. So, all right, Coulomb, I agree. So 1 over, so d equal to 3 Coulomb. So all right, x12 are
হ্যাঁ স্যার, ওই মানে ইম্পর্টেন্ট ফ্যাক্টরটা তো 1 ওভার mod x ই হচ্ছে, মানে মানে ওটার সাথে আর কোনো টার্ম থাকবে মানে?
এইবার এইটা তো ভাবো একটুক্ষণ যে আর কিছু থাকবে কি থাকবে না।
হ্যাঁ স্যার, মানে ওই হ্যাঁ স্যার করে বলছি।
আরে না করে বলো না বাবা, মানে যে থাকবে কি থাকবে না, এত তো হলো, পোল ফোল বললে বললে তারপরে
স্যার থাকবে,
হ্যাঁ ই টু দ্য পাওয়ার,
হ্যাঁ 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 ই পাওয়ার, হ্যাঁ হ্যাঁ ওই পোলটার জন্য পাওয়ার আই কে তে, হ্যাঁ হ্যাঁ হ্যাঁ
ভেরি গুড, অলরাইট।
ই পাওয়ার আই কে।
এবার কে এর সাথে কি কি গুণ হবে?
স্যার একটা মাস স্কেল, মানে ইনভার্স মাস স্কেল, স্যার মড অফ x1 মাইনাস x2 ই পাওয়ার k মড অফ x1 মাইনাস x2। স্যার কারণ k ডিমেনশনটা স্যার 1 বাই লেন্থ, তো ওটার সঙ্গে একটা লেন্থ ফ্যাক্টর থাকবে, মানে
সরি x12 তার সাথে কি গুণ হবে?
স্যার একটা মাস ফ্যাক্টর থাকবে স্যার, কারণ ওটা ইনভার্স লেন্থ হচ্ছে, মানে
আমাকে এইটা বলো যে এই এর টার্মসে কি থাকবে?
স্যার একটা স্যার একটা এ থাকবে, এ স্যার মানে বাই এ থাকবে স্যার, কারণ এটা তো মানে না, এটা হচ্ছে ইনভার্স লেন্থ, হ্যাঁ মানে বাই স্যার বাই স্কোয়ার রুট অফ এ অমনি কিছু একটা থাকবে। হ্যাঁ হ্যাঁ সো ইনটু স্কোয়ার রুট, হ্যাঁ ইনটু
No, you close the poll in the उससे सेट की टोपट so e to the power minus x12 square root of a. So what is square root of a? It obviously has the physical dimension of inverse length. So I can write this as e to the power minus x12 over xi divided by x12. So that is the three-dimensional correlation function. So d equal to 3, this is the answer, and that is that. So d equal to 3, the two-point function in coordinate space looks like this, and it falls off with, this is the mass term essentially. So it falls off with increasing x, and the scale is xi. Xi is the correlation length, which is the spatial scale of the problem. This problem is scale free at the critical point, because xi is equal to 1 over square root of a equal to 1 over t minus tc to the power half. So at the critical point, this correlation length becomes infinitely big. This goes away. A equal to 0. It's the Coulomb problem, and the answer is 1 over x12. So long range Coulomb force, Coulomb-like at 1 over x12. The system is now scale free. The scale had been set by the correlation length. I mean, if xi goes to infinity, so what does scale free mean? Scale free means that if I'm actually, the gx12 is something I can measure, and the point is that if I am at x12, so this is, I'm plotting against x12, this is 10 and this is 20. And on this side over here, I'm plotting, let's say, this correlation function, which I've called g x12. If this term is not 0, then, all right, let me have 5 over here. So 5, 10, 20, I'm plotting this up. If this is not 0 over, then you notice that the function drops like this, which means that between 5 and 10, it drops by a certain factor, but between 10 and 20, which is also a factor of 2, it drops by a completely different factor. And it is e to the power, so you can imagine that if at 5 it was something, 10 it may still be something, but at 20 it is nothing. So the drop over here is e to the power minus 5. The drop over here is e to the power minus 10. But when it is a power law, in this case over here, you go from 1 over 5 to 1 over 10 to 1 over 20. It is always, for this equal spacings, equal fall. So there is no scale. I can't set a scale over here. Everywhere I look at the system, if I use a magnifying glass, I can take it to the other part. So that is what the scale invariance is all about. the system is scale free at t equal to tc and has a scale which is the correlation length of the system at at temperatures which are not Tc and whether above or whether below, and therefore the psi, the correlation length, behaves as T minus Tc, has a divergence T minus Tc to the power minus. So we have introduced a new till now we have talked about alpha, beta, gamma, delta, right? Specific heat, magnetization, susceptibility, and T equal to Tc. How does M depend on H? Now you have a new one. Now this is, you are beginning to probe something different. You are actually probing light scattering or a neutron scattering experiment on this system. And that is giving rise to it is a non-local issue and is giving rise to the actually picturing the correlations at different scales, and that scale which diverges at when you have a scale-free system at T equal to Tc and psi is T minus. So that defines the correlation length exponent, which is new. Very good. But now, so let's go back to the susceptibility. The susceptibility is integral ddx, and this integration over the correlation function g of so x, right? Mod x. So chi is this integral which is over this. Gx is, this g is a function of actually x over psi, and therefore the g is a let's write it in this fashion, that the correlation length, so g is actually so it's the all right, I could have come from here that phi k, phi minus k, the susceptibility, this is it's the k equal to 0 part, which is this a over here. You would have normally done this integral, the g of x, is k square plus a. You would have done so e to the power minus x over psi divided by its I did not do the all right, sorry, yeah, 1 minute, got ahead of, I did not mention I did this d equal to 3 calculation. Because I wanted to ask you the question. So we did it for d equal to 2 and got the answer that it is e to the power minus x over d equal to 3, and it is e to the power minus x. Now, what is it for d equal for any other d? For any other d, the answer, I mean, here is the thing given over here. G of x12 is ddk e to the power ik dot x, and it would be some, we had to multiply by something which looks like e to the power minus x over xi, and roughly it will always be something like that. And the power over here, if it is a d-dimensional system, the power would have to be d minus 2, because the is ddk e to the power ik dot r over k square plus a. So k square plus a, if I just power count, imagine, just forget the a, power count in k. The power count in a tells me that this is like 1, this integral has to look like 1 over k to the power 2 minus d. So if k, it's like a to the power 2 minus d, then the your k is the, so that's the power count of this. What did I do? It is k to the power, it's k to the power d minus, its power count is k to the power d minus 2 of this integral over here, from which I can get that it is like, I mean, 1 over r to the power 2 minus d minus 2, the power count over here, that is d over 3, and then, all right, let me stop for a moment, that it is k to the power d minus 2, and that is exactly what you said when it was d equal to 3, that it is going to be like 1 over k. If it is going to be any other d, for example, d equal to 4, it would be like 1 over k square. D equal to 2, it is logarithmically divergent when you see over here. So general structure is k to the power d minus 2. So g of so this part, what you do when you do this integration over the dimension is d to the k to the power d minus 2. K has the dimension of 1 over x, so the 1 over x would be, it is 1 over x to the power d minus 2. So g of x would, I mean, this e to the power mod x which you have for d equal to 3 would go to d minus 2. So that would go to d minus 2, which means that over here, I mean, this is all for power counting. The exact, the form of the integral would be very different and so on and so forth. I'm not bothered with that. I'm just power counting. The power has to be 1 over x to the power d minus 2. The rest of it has to be a function of x over xi, which has no power. So it is e to the power x minus, that's the correlator over here, which is g of x12. So g of x12 is, and now I have to get the susceptibility. The susceptibility chi is integral e to the power minus x over xi, x to the power d minus 2, and then it is integration over the it's phi x minus phi x phi y integrated over all space, which is integral over ddx. So you set the, so you want to get the xi dependence. You want to get the xi dependence.
Scale out for the u times
Scale out.
xi.
And so it is xi square. So chi is equal to xi square. which means that this is proportional to t minus tc to the power minus 2 nu. So xi, I have just introduced the exponent nu by saying that it is t minus tc to the power minus nu. The answer is that this susceptibility then in terms of the nu is t minus tc to the power minus 2 nu, and the susceptibility goes as t minus tc to the power minus gamma, and therefore you get gamma equal to 2 nu, right? So all the exponents are probably not independent of each other, and you pick up this equal just from the thermodynamic relationships, you come up with this answer that gamma is equal to 2 nu. Correct? So, well, is it right? Now, way back in the 40s, Onsager had exact solution for the d equal to 2 Ising model. The exponent, the susceptibility exponent was, the susceptibility behavior came later. This was Yang, sometime I think in the 50s. And the susceptibility of the d equal to 2 Ising model, so d equal to 2 Ising gamma was calculated, and exact answer is 1.75. Onsager had the exact nu, which is nu equal to 1. So you have a problem. All gone. Exact, here I have given you an argument, nothing much to be, nothing much is wrong with it. I mean, nothing is wrong with it. What is nothing much? I mean, I took a form like d minus 2. I showed you that you can do a bit of Fourier transforming this and that, get that answer. So d minus, wrote it down, and here is the d equal to 2 Ising model, where gamma is known and eta is nu is known, and it doesn't fit. So what is missing is an exponent which I have not told you about. So if I actually sit at the critical point and measure the at t equal to tc, actually look at the correlation function, it does not behave as 1 over x to the power d minus 2. The answer is actually g at t equal to tc goes as 1 over, so g of x is 1 over x to the power d minus 2. You have to introduce anomalous dimension in the problem, that there is an extra dimension which the exact solution could find for you, but these playing around with the Gaussian, what we have been doing is playing around with a Gaussian model. Playing around with a Gaussian model does not give you the liberty to say that this behavior is going to be true in all dimensions. It is obviously wrong in d equal to 2. And therefore, I need to have a new exponent eta, because of this reason, generally called the anomalous dimension. So that people had not why? I mean, this whole business was a little neutron scattering people, light scattering people were doing experiments in d equal to 3. And they never complained. You see, the point is that they never complained about the fact that this was not 1 over x to the power d minus. So that it was not 1 over x was not a complaint from these people who have been doing neutron scattering all through the 60s and light scattering from even before that, 50s, 60s and so on. The reason being that in d equal to 3, eta is of order 10 to the power minus 2.
Adding a fractional or a small decimal number to it.
No, I mean, you are adding it to 2.
Now, you mentioned the numbers, you mentioned is okay, but for fractional dimension.
There's no fractional dimension. I mean, it's d equal to 3. The expected answer in d equal to 3 is 3 minus d minus 2. Or d equal to in d equal to 2 in d dimensional space, the expected answer is d minus 2. But I mean, the 2 was your imagination, right? I mean, you took some argument like that and said a Gaussian model gives d minus 2, therefore the answer is d minus 2. So all that is being said that the Gaussian model is not a right thing. People did not suspect for a long time that Gaussian model is rubbish even above t equal to tc, because this, I mean, things seem to work out here over here, and there were other issues involved. Obviously, the chi, which is the light scattering and neutron scattering people knew that chi is not equal to 1. So they knew very well that chi is, but there they were not unhappy because of a reason which I'll show you immediately. So till now, I mean, what we have is that you are forced to talk about, there was this d equal to 2ising, which was saying that this d minus 2 can't be right. I mean, certainly not in d equal to 2. So, and then you say that, all right, if I have to be consistent, then if I have to honor the fact that it is not 0 in d equal to 2, then let me put in, I mean, all right, let me put in eta, which is a correction. And then eta in d equal to 2 is 1/4. But experiments show that d equal to 3, eta, I mean, so for a long time people believed that it's, I mean, everything is fine. I mean, the standard d minus 2 is great. So the resolution when finally Wilson calculated things was that eta turned out, I mean, that was the exponent which nobody else could touch. And Wilson RG could calculate the eta and calculated eta and found that it was of the order of 10 to the power minus 2, predicted it, light scattering techniques, and in the subsequent decade were improved by an order of magnitude, and the small exponent was picked up. So that is, I mean, the perfect combination between theory and experiment. There was the warning coming from Unsaga, that something is wrong. Experiments 50s and 60s said, no, I mean, it's d minus 2 in d equal to 3. And then you finally, I mean, somebody pays heed to all sorts of anomalies that could be there, and out comes a method of actually calculating beyond the Gaussian model. The problem was that beyond the Gaussian model, you could not calculate. Well, why couldn't you? I mean, 5-foot theory was known to high energy physicists for ages, essentially. Or, all right, I mean, QED was known for ages, I mean, since the 40s, and scalar field theories were also known. So why couldn't you calculate? Why you could not calculate was there were divergences. Divergences in high energy come from the large K region. Divergences in critical phenomena come from the small k region. So the theory calculation, I mean, people knew how to tame infinities in high energy physics, but it was all at high k. This was a problem. You are not talking about high, you are talking about very small k. It is long distance phenomena. It is large distance correlation. We are talking about a correlation length which is infinitely big. So you are talking about large distance scales. So whereas high energy is all short distance scales. So you know, I mean, what Feynman, Schwinger, etc., Tomonaga did was to control that, the renormalization which controlled that. This was a very different kind of beast and had to be done very differently. So that was the Wilson contribution of how to actually set up the renormalization scheme which works at high, and the fact that they all look the same emerged over the next couple of decades, that the same kind of thinking can take you to, I mean, both of them belong to the same class of theory, removal of infinities. So but in the early 70s, you had a problem. You had a problem that, I mean, there was on Sagar with eta, which is 1/4. There were the experimentalists saying there is no eta in d equal to 3. And any theory which makes sense has to tell you that the whatever Onsager calculation in d equal to 2 has to agree with whatever the theory calculates in d equal to 2. Onsager d equal to 2 and the d equal to has to agree. So that was the, I mean, you get a experiments, not even numerics. I mean, even today, I mean, doing light scattering in d equal to 2 or neutron scattering is not trivial, is non-trivial. So, so that completes the dimensional question of exponents, that this is the anomalous dimension exponent. So you have alpha, beta, gamma, delta, nu. So that for the conventional critical phenomena, that is the story. And well, what happened that it is x to the 2 plus eta. So chi, this relation which we wrote down, which we got as chi equal to 2 times nu, goes to chi equal to 2 minus eta. Hmm? Oh, that was when eta was in the air because of Onsager, but the calculational tool, it could be calculated only after Wilson introduced it. Uh-huh. So, all right. So now, I mean, what you notice is that we have these things over here, but it is not quite that they are all sort of independent of each other. That you see a immediate connection that chi is equal to 2 minus eta times b. So maybe there are others. So that so the next thing that one wants to get at is that are there easily accessible are there easily accessible relations which you can now let's think of it somewhat differently, that F, the specific heat, is T del to F T square. So this is, well, at least over here, that comes with a negative sign, right? Or no? Give or take the sign. Huh? It is there is a negative sign, I think, because df is equal to dE minus TdS. So it is minus SDT minus TdS. dE minus SDT minus TdS, and therefore it is S is equal to minus del F del T at constant V, and then you take it. So there is a minus. So, all right. I mean, C is minus T del to F del T square. I mean, the negative sign is certainly there, but not really going to be important for us. But so as I told you, this is, I mean, the same as, so far as our business goes, as minus TC del to F del T square. This derivative that we are talking about is essentially a derivative with respect to T minus Tc. So that is the derivative, I mean, that one is talking about over. It's del T squared, the del T squared, because, I mean, the F, simply because the F is a function, the part of F that I'm interested in is a function of T minus Tc, and therefore the derivative is. So what is this F? Well, C I know is like this is T minus Tc to the power minus alpha. So the consistency over here means that F has to be like T minus Tc to the power 2 minus alpha. I mean, all that I've just multiplied by T squared. So F has to be like T minus Tc to the. So this is with no external field. What if I have an external field? Now the F is going to be T minus Tc to the power 2 minus alpha and some function of h. What kind of a function? It has to be such a function that the magnetization has to go as t to the power beta. T is t minus tc over tc. It's convenient to work entirely in terms of the dimensionless stuff, so that's so m is t. So I want this thing, the magnetization, to be like t to the power beta. Now, what is the magnetization? The magnetization is m is del f del h. So if I take a derivative over here, I should get, and it is zero field magnet, the spontaneous magnetization. So del f del h at h equal to 0. So f is equal to t minus tc, t minus this chi should have been gamma, right? Well, it's a susceptibility. I mean, the index is gamma. So it's h, and now I want, where was I? Del f del h at h going to 0. That is the magnet. So the point is, I would have to take a derivative with respect to this, and it has to be a scaling variable, right? Because the thing has to be such that if h is equal to 0, it has to come back to this, which is all right, that becomes a constant. But now it has to be also that there has to be a t to the power, let's say, some x, so that when I take a derivative, del f derivative with respect to h, I have to get this t to the power beta back. So it has to be a function of some h over tx, and so if I do that, then so I take a derivative, m is t to the power, so this is t to the power 2 minus alpha, and then it is 1 over t to the power x, f prime of h over t to the power x. This goes to 0, so f prime becomes a constant, and this you want as t to the power beta. So beta has to be 2 minus alpha minus x. So x is equal to 2 minus alpha. X is equal to 2 minus alpha minus beta. So the structure of this f is equal to 2 minus alpha minus beta. If I have that, একটা TC থাকবে, sure, but TC is a constant. TC টা তো মানে হ্যাঁ, বলো। F of 0 is a number. Is also a number. So the statement then is that the form of f has to be, so if I just write this as t to the power This was 2 minus alpha. So t to the power 2 minus alpha. And then if f has this structure over here, I know that h equal to 0 gives me the right answer. M equal to del f del h at h equal to 0 gives me the right answer. But now I need to know whether for example, do I get the right answer for the susceptibility? So I have to go two derivatives and then, so the susceptibility is del m del h as h goes to 0. So I get the m by this relation over here. So m is t to the power alpha, so it becomes t to the power beta, and then it is f prime, and it is h over 2 minus alpha minus beta. So I have to take, to get the susceptibility, I have to take a derivative once again. So to get the susceptibility, it is another derivative. So chi is equal to t to the power beta, and then you have f double prime. So it is f double prime of h over t to the power minus alpha minus beta, and then it is your a derivative of this. So it is 1 over t to the power 2 minus alpha minus beta. So h equal to 0, chi at h equal to 0 is equal to, this becomes a constant, so this is proportional to t to the power 2 beta plus alpha minus 2. But this by definition is like t to the power minus gamma. And therefore, gamma plus 2 beta plus alpha is equal to 2. So you make use of this structure just from the, you have defined the exponents, you have got, so to get all the things, at least, I mean, the magnetization come out right, the free energy comes out right, the magnetization comes out right, if the free energy has a structure like this. And then you take that structure and you say, all right, let's see what happens to the susceptibility. So you calculate the susceptibility, and if the answer comes that this is equal to 2. So now the point is, all right, test one-dimensionalizing model, a two-dimensionalizing model once again. Does it do it? Gamma is 1.75, beta is 1 over 8, alpha is 0. It's a logarithmic specific heat. So so that's your 7 by 4 plus here is 1 by 4, and that's satisfied. The fluid people who were doing experiments for gamma, they were picking up something like 1.2, somewhere between now the dust has settled on 1.246 something, so on. But I mean, roughly, let's say like 1.25. The beta, so this is D equal to 3 fluids and 1.25 for gamma. Beta was approximately 0.32 and alpha was about 0.1. So that was the situation for the experiments over there. So you can see 0.64, 0.74 and 1.25. So once again, quite equal.
Because here we see that alpha, beta, and gamma and beta and mu is so what about delta? Delta is
no, I mean, you will be picking up, you can now go ahead. I mean, All right. To get the delta, I mean, since you asked for it, let's find out. You have delta is mh is h to the power 1 over delta at t equal to tc. So you can take it as that if this is how are you going to get the delta comes out. I mean, I think the it is beta into delta plus 1 is
Gamma
2
equals
minus gamma. It's 2 minus alpha. I think it's 2 minus alpha alpha plus beta plus delta 1 is this, and therefore gamma plus 2 beta is I think it is beta into delta plus 1, which works out to be if I make use of or I have to get the delta into this.
Sir.
Yeah.
Sir, স্যার বলছি আমরা যদি জিটা ধরি স্যার স্যার তবে তো জি এরও তো একটা স্কেলিং ফর্ম থাকবে স্যার মানে ওই কোরিলেশন ফাংশন
রাইট হ্যাঁ
স্যার কিন্তু ওটার মধ্যে তো ডি আছে স্যার মানে ডাইমেনশন আছে স্যার তো
but the dimension goes
তো স্যার তো এমনও একটা স্কেলিং ল স্যার থাকা উচিত মানে যেটার মধ্যে ডাইমেনশন থাকবে.
All the physical quantity is chi, which is g x ddx. No, that is the so the d that you see over here when it cancels out, and so the explicit d eshe boshe na dita ashe d does enter the calculation of exponents, gamma, new era, shobai spatial dimension dependent, but that for a different reason. Yeah, a problem of getting into the the definition is going to go off. A definition does not happen. But I guess what you are trying to say is something slightly different. Je extensivity ittadi byaparer ki holo. It is really a question of extensivity, extensive property, intensive property. Tara ki ektu shekhane ki jhamela ache, and the answer is ache, and we will deal with it. Yeah.
Achha.
So yes, right, but I'm sure what you were এইখানে d কেটে যাওয়া that is trivial, but yes, there is a question of what is extensive extensive ব্যাপারটার breakdown normal everything is being determined by a correlation length. And if it is being determined by a correlation length, tale amar extensivity nei. Right? I mean, if thermodynamic quantities like the susceptibility are going to be determined by a correlation length, tar mane to tar extensivity holo na. আমি লিখলাম chi is equal to volume gx12 ddx12, right? This is what লেখা হয়েছিল, and I said I am very happy because এইখানে এই the chi should be extensive, and extensive volume টা বেরিয়ে এসছে. এইবারে I am looking at this, এটা তো correlation length এর উপর নির্ভর করে, so there is a length which has come in.
হ্যাঁ স্যার ওটাই ডাউট ছিল স্যার মানে
Right. ঠিক একেবারে, that's a right doubt, and it is true, and we will have to address that issue. একদম।
আচ্ছা 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 স্যার
You see, মানে যে হলো না, মানে আমি তো ভিটা বার করে দিয়েছি, তারপরে তো লেন্থসরা বেরিয়ে গেছে, ডাইমেনশনটা তো বেরিয়ে গেছে, আমি তো একটা ডাইমেনশন নিয়ে বাট তারপরে আমি বলছি যে না না, ডাইমেনশন বেরোয়নি, ওটা ডিপেন্ডস অন দ্য কোরিলেশন লেন্থ, right? Yeah, right. So good point to stop. Bolo, over here, and yeah, we will have to address it. Yes, absolutely.